So the task before us now is to take the situation from this classical mechanics point of view and to contrast it with what we know about the real or quantum world and to begin to develop a true quantum mechanics. And our discussion, as you can see, is going to follow and parallel exactly what we've seen here in classical mechanics. So the first topic then really for us to discuss are what actually are the observables in quantum mechanics. What are the things that we actually are going to go out there with our instruments and take a look at? Now, the observables in quantum mechanics, the ones that we are going to begin with, actually are very similar to those from classical mechanics. And the reason is that classical mechanics envisions the world as a series of featureless point particles. And in our description of our sort of Empedoclean view of the world, we have the electrons and the nuclei, which we can treat to very high accuracy as simply point particles. We are not concerned about any internal structure to those particles. So for us, we are going to, in physics 3316 here, we are actually going to focus also on featureless or point particles that are featureless or have really no internal structure to them. That means, right, that we are going to have the same types of things that we go out and measure. And we've already been talking about these in all of the quantum experiments. We are still looking at what are the positions of the particles in our system? What are their momenta? We also could, though we haven't spoken much about it, we could also think about the angular momenta of our particles. And certainly, though, we also have been thinking a lot about the energy, or more specifically, really, the Hamiltonian, again, associated with our system. So we have a very similar structure here. I do want to point out, though, that there are also other observables that do come up in quantum mechanics, that actually the particles in our world do have internal degrees of freedom and internal structure. We simply just aren't going to be focusing on them much in physics 3316. We've got quite a lot on our plate already to get a good handle on position and momenta. And as I've said, from an Empedoclean point of view, we can actually do a whole lot with even just those. So that's going to be our focus. But I didn't want to go forward without mentioning that there are other internal variables in particles, and these are out there for us to discover, scientifically as we go on and look more deeply at our world. One very important degree of freedom that will come up probably toward the end of this course when we get to atomic structure is the internal variable called spin. It turns out the electron has something called a variable called spin. It's not really like a classical picture. You're picturing like a classical top, but it has some similar features, so it's given that name, spin. But there's all kinds of other variables that you can learn about as you study more in depth all the different quantum particles. Who knows? There are other variables like lepton number. There's a whole set of these, right, that you will learn about later, but our focus is going to be on this same point particle set. Now, as we focus on that set then, I think we've got a pretty good handle on what our observables are. Measurement, though, clearly is going to be a bit of a more tricky issue, because we've learned that we have this underlying sort of randomness in the world around us. So this is definitely going to be different. We have things like Heisenberg uncertainty principle. So this is where our thinking is really going to begin. So to try to understand measurement, and I'd like to make some illustrations based on things that we now know through the de Broglie hypothesis really happen. So to try to draw out these concepts, I'm going to invent sort of a device that will allow us to carry out measurements on systems. So my device is basically going to be a box, and I'll have a lid that I can put on my box to close my box, and I'm going to put some particles in here. right? Or it's just maybe even a single particle, and I'm going to wait a long, long time until, as we've said, it eventually gives off all of its energy and ends up in its lowest energy state, and I'm going to hope that has prepared the system into a particular quantum state, this lowest energy state. And then I want to go and see if I can determine whether or not I've got two systems in the same state. So I will take two systems, and I might prepare them slightly differently. Maybe I'm trying to figure out how long it is I actually have to wait to get into the true quantum ground state. So maybe my other system is prepared with a different waiting time, something like that. And then, to try to figure out what state these systems are in, I will do my experiment by suddenly removing the little cover and sticking in its place a photo plate right in front of it, to detect then where the particles are when they emerge from my system. And if I have these two systems, I could do a measurement somewhat like this, and maybe in the first system the particle ends up sort of near the top, and in the second system the particle ends up sort of near the bottom. Now, we can ask, are these in the same state? And there's basically sort of three different answers we could give to this question, right? It could be that we would say, yes, they must be in the same state. Or we could say, no, definitely they are not in the same state. Or we could say that we don't have enough information yet, insufficient information. Or I could just say, we don't know, we can't tell. Actually, maybe more fundamentally, instead of just we don't know, that's the state of our knowledge, we'll say we can't tell. So, if I look at this, of course, from the classical point of view, it's pretty obvious. I've done an experiment. I've measured the positions of these particles. I got different answers. These must have been in a different state. The quantum mechanical point of view, though, is clearly quite different. This sort of situation, where fundamentally the particles end up landing at different positions, should be very familiar to us, right? We've seen this all the time, like in the G.P. Thomson experiment, where the electrons land completely randomly, but overall they build up a certain pattern, right? So we would say, from the quantum case, the answer is that we just can't tell. We have to determine something different in order to determine whether or not these are in the same state, because this is just a normal sort of happenstance. So I hope what you can see is that what we need to determine here really is not whether or not an individual measurement gives me different results, but the question really is, am I going to get the same probability distribution? So measurement now is not going out and finding a single thing. Measurement now has to be generalized in quantum mechanics to finding the probability distribution associated with a variable. Maybe, so this is just one example, right? So e.g., right, because it's an example. My previous example was go in classical physics and just find the position of the particle. Now what we have to find is not the position of the particle, but the probability distribution for the particle. That is really the fundamental difference. Now, we are about to embark on a formal theory. We're going to be talking about these types of probability distributions, so I thought we should spend a little time defining them a little more precisely. You know, I've been drawing these pictures of some probability distribution as a function of x. I might have some kind of a peak like this. And you will notice this is not quite the ordinary probability that you're familiar with probably from your simple, simple basic probability where you're counting balls and boxes. This is a little bit different because it's a function of a continuous variable. Now, though, we know how to handle it. We've been talking about this, all semester. Basically, what we do to get a nice, smooth, continuous function like this is we have been dividing space into a series of very narrow bins, right? So maybe my bin goes from position x0 here to position x0 plus some small amount dx, right? And then we just count how many particles end up in this little sliver. So what we are really saying when we talk about the height of this probability distribution, the probability distribution at point x0, that would be the height of this little rectangle. But what really represents the number of particles landing there is the area under a curve like this, right? So the probability distribution at x0 times that length That we are actually defining as the probability that we find particles landing inside that particular piece of the histogram. So x is between x0 and x0 plus dx. Now, the last comment I'll make is you will notice that this probability function itself, right, has some interesting units, right? When I multiply it by dx, I get the probability that my particles are landing in a given bin. And you can see that has to be proportional to dx, because clearly if I doubled the width of my bin, I should expect basically twice the probability, or twice as many particles to land in that region. So what we're really looking at for this probability function is a probability, right, divided by dx. It's really a probability per unit length. So the units are probability per length, and this kind of quantity then we call not a probability, but a probability density, because it's probability per unit length. And that's why I've been writing it with this kind of a curly P type of a picture. Now, with this in mind, that we're actually talking about probabilities, we can now ask a similar question to our measurement, but we're going to be a little bit more sophisticated now. I'm going to have my two, experiments where I have collections of systems that now have been prepared under two different types of preparation, maybe a long time, maybe, and a shorter time, to see if I'm still in the same ground quantum state. And then what I'm going to be measuring now, though, is not where a single particle lands, but what I want to measure now is the probability distribution for where they land. And it might be that for my two systems, I find one of them has a peak near the top half, right? Probability versus x and x. And the other one has its peak near the bottom half, right? And now this is clearly, definitely not the same state, because we're getting now different distributions. And it could be that, for instance, this is why we got the experiments that we saw here. That simply they were predestined to kind of land in different regions because we were coming from different states. Now, I can go a little further, though. Let's suppose we have a situation where I've got my boxes, and again, I measure these probability distributions for my boxes, like so. But now let's suppose when I measure probability of x versus x for the two systems, I end up with beautiful, identical, curves, maybe both centered. They're supposed to look the same, right? Centered right on the middle of the box. And then the question is, are these then in the same state if the probabilities are the same? Now, in this case, if we ask that question, you might be tempted at first to say yes. Well, we're getting the same distribution, and that's what really describes the behavior of the system, but we really, it turns out, can't tell. We still can't tell. And the reason for that is that the definition itself, fundamentally, of state talks about the outcomes of all experiments. So for us, experiment is now measuring the measurement means finding the probability distribution, but we haven't done it for all of our possible observables, right? It could well have been that the momenta of the particles coming out of these boxes were different. And you guys know how to measure that. What you do is you take a screen that's much further away than the size of the mouth of the box here, right? So that where the particles land now is that angle is really not so much determined by exactly where they came out of the box, but more by their direction of travel, namely their momentum in that x direction. And we could have probabilities, I'm running out of space on my screen, probability distributions for that momentum in the x direction. And that might be maybe this one has it peaked up high, and then this one, if I'm looking at the probability for the x momentum, might have most of the particles far away landing down low, telling us there was a downward component on average to the particles. So this would be the straight over line. So we could see then these distributions for momenta were different, and now that would be information that would tell us that it's not the same state. So really, we need to know the outcomes of all of these different probability distributions to make a rational determination of the state of the system. Now, as we're going along here, I want to be very careful with my notation. As I've said, I'm writing a curly p here because this is a probability density, not an ordinary probability, right? It's a probability per unit length. And it's something very similar here, but this function is a function of momentum, which is why it's written as a function of p, but I don't want to imply that it's the same functional shape, right? This shape of this function could be quite different from the shape of the function that describes the distribution in x. And since these are really functions describing different things, we really should have different names. I like the curly p because that tells me it's a probability density, but this is probability not per unit length like this probability density. This is probability per unit momenta. So it should have a different name. And so for things that have to do with momenta, I'm going to use a tilde on top of those variables, just so that we can keep everything straight and clear. So that refers to momenta. So it means it's a momenta is what I will be using that tilde for. Right. And we're going to be very careful in our notation like this at first until you get used to it. It's like when you first learn mechanics and you're first using vectors, you're always super careful to put the vector hat on top of everything. After a while, you get used to what the variables mean, and we don't have to be quite so pedantic and have such super careful notation. But for now, I think that would be a very good idea. Okay, very good. So now we've got an idea really of what measurement means, and we've discussed somewhat what it takes to know the state of a system. So measurement is finding the distribution for an observable. So we can move along in our program now to start asking what the minimal specification of a quantum state. So I will ask that. Again, by specification, I'm implying I want the most convenient way to do it. So the minimal specification of a state, we saw that, well, it looked like we might need, if our basic observables, and again, this is the momentum distribution with my tilde, both x and for the momenta, say in the x direction, if I'm just thinking about a one-dimensional system. It might be that we need that much information to specify the state of the system. Now, it's also possible, theoretically, if you think about it, that we could do better. Maybe we only need to know the probability distribution in x. Now, I just gave you a counterexample here, which said that, well, if I have a given x distribution, I might go and do a measurement and get a different momentum distribution, and then these wouldn't be in the same state, that we had to go and do these experiments. But there might be some mathematical connections between the x distribution and the momentum distribution. We know already of one such relation. There's the Heisenberg uncertainty principle that tells us that these probability distributions have some relations among them. So there might be some mathematical trick whereby just knowing p of x, we might be able to determine p tilde of p to get the momentum distribution. So that's a possibility we are going to have to begin to investigate. Or who knows, it might be something else, right? Instead of needing these two functions, maybe this function's not enough, but maybe there's another function out there that's good enough to get us the results of both the x and the momentum distributions. Who knows? Maybe that's this quantum amplitude thing, this quantum wave function that we've been talking about. That's one of the things we're going to be focusing on in just a moment. Now, in addition to the specification of a state, the last item on our list was, of course, the question of determinism. And so here we have, if we think carefully what determinism means for us, it means if we know the state of the system at one time, can we predict the state of the system at a future time? Now, I want you to notice that if you took a classical perspective on what a state was, you wouldn't have determinism, because just knowing the state of the system doesn't tell us where any particle might be detected, right? That's fundamentally random. But we have a chance that what we can predict is the future distribution of the results of experiments. And that then is what constitutes the idea of determinism in quantum theory. So for example, maybe if we know the probability distribution for the position at time t equals 0, and know the probability distribution for momentum measurements at time t equals 0, who knows? Maybe that is sufficient to determine for us the state of the system, and if maybe momentum and position distributions determine the state of the system, maybe that would be enough to tell us the outcome of the probability measurements at time t and the outcome of the momentum measurements in the x direction at time t as well. These are the issues that we are now going to begin to investigate as we study our quantum mechanics.